Okay, I'm going to revisit section 6.3 for you guys because I really feel like this is the highlight of the new chapter's new material. Dividing polynomials, and that means long division and synthetic division. With polynomials, of course. Now, the reason I say that is because if you think about everything else in our chapter, with one exception, which is multiplicities, but if you think about things such as x-intercepts and y-intercepts, if you think about quadratics with factoring, simplifying radicals, and imaginary numbers, etc., etc., even sum and difference of two cubes. Because the thing about this is it's a property with which you apply some stuff, and this came from dividing polynomials. Because if you remember section 6.4, when we talked about that, that's the origin of it. We use division to make it happen. So all the stuff is the basis of it. Now the other one is multiplicities. That's kind of a new subject if you think about it. But the dividing's the big one that I really want to make sure that we get. So it's an expanded overview that we'll do here. I'm going to start by doing long division practice with these two guys right here. 2,807 by 9. And 377 divided by 13. Okay. Now, this number, what you do is, and everybody does syntax differently. But what you're going to do is you're going to take that 9 and see how many times it goes into this 2 right here. Now 9 doesn't go into 2 any sort of times. So you go over and you look at 28 instead. Now what we're really doing when we do division is I'm not seeing how many times 9 went into 2. I'm seeing how many times 9 went into 2,000. Okay? The answer to that is if it's a 0, it doesn't go in any times. That means my answer is not in the thousands. Okay, so you're looking to see how many times 9 goes into 2,000. It doesn't go in any times. It goes in a certain amount of times, but in the hundreds. That's why we check 9 with 28. We check with 2,800. So we check that, and it goes into 28 3 times. So we know our answer is 300 something, because 9 times 300 something is 2,700 something, unless it goes a little higher. So 9 times 3 is 27. That's why we subtract right here, 27, and we get 1. Now 9 should not go into 1 at all, because this is 9. How many times does 9 go into your 100 value in terms of hundreds? The answer is 0. So you're going to bring down this 0 here to say how many times 9 goes into 100 in terms of your tens place. So that's our check right here. 9 goes into 10 once. This number is not a 1. This number is a 10. So this answer is 300 and something in the teens. 10 something. 9 times 1 is 9. Subtract, you get 1 again. And bring down the 7. You know what? I believe I wanted this to be an 8. I want this to be a clean number. So if you'll excuse me for 1 second here, let's make this an 8. Make that an 8. You're just following along anyway, so follow along with what I put here. How many times does 9 go into 18? Now this number is actually 18. This is in the 8 is in the ones place, so this is 2 times. 9 times 2 is 18. And subtracting, you get 0. So your answer is 312. Or another way of putting it, 9 times 312 equals 2808. Okay, so remember, when you divide this by this number and get this, these are two factors of yours of 2808. Okay, I'll do it one more time. Now I'm doing it by 13. Now the important thing here, the difference between doing numerical division and polynomial division is in numerical division, your units digits leak into your tens digits. For instance, I count up 1, 2, 3, 4, 5, 6, 7, 8, 9. Then my next number is 10. So it goes in my tens digits. So 1, acting as 10 here, is my most significant digit. But the 3 also matters. So I need to check and see how many times this whole number goes into these numbers here. So 13 doesn't go into 300 any 100 number of times. So you know your answer is a 2-digit number. 13 goes into 37, however, or 370, some tens number of times. That's 2 times. 13 times 2 is 26. Subtract that and you get 11. And you bring down the 7 here. Now again, 13 shouldn't have gone into 11. If it did, then you didn't count enough tens in here. Remember, this number's not 2, it's 20. How many times does 13 go into 117? I think it's 9. 13 times 9 is 117. Subtract, you get 0. So your answer is 29. So again, 377 equals 13 times 29. These are two of your factors right here. This 0 acts as your remainder, and I'm going to talk about remainders later. Okay, let's talk about polynomial long division. Now, this is a lot that's written, so I'll read through it. I'll see if I can make sense as I do the problems, and we'll be good to go. In polynomial long division, the most significant term, the one with the highest degree, is the only important term. So when it comes to doing division, you know when I talked about here that this 1 was super important? Well, the 3 matters as well in numerical division because this number is one individual thing. 13 is 10 plus 3 here. But the 3 matters because your unit digits leak into tens digits. See, unlike numbers in our decimal system, digits can't leak over. I should have said terms can't leak over. In our decimal system, digits can leak over. 10 ones become a 10, 10 tens become 100, 10 hundreds become 1,000, etc. So no amount of x's can ever be as significant as an x squared. So for instance, let's say we had x squared plus 99999x. We're dividing something by that thing right there. This is the only thing that matters. How many times does this go into it? This many x's means nothing compared to this x squared. And that's the thing that matters. X squared is your most significant term. Remember that x's are just numbers. Okay? That's all they are. Okay, in terms of doing long division, so let's get this started. I'll go back because we're going to run through this as we go. X cubed plus 27 divided by x plus 3. What I'm going to do, I'm doing this divided by this. What I said was treat only your most significant digits, the only thing that matters. This 3, any number of constants has nothing to do with how significant your linear term is. And I need to see how many times this goes into every guy that we add or subtract here. Okay? So, treat everything else as you would numerical long division, down to multiplying your divisor by your quotient values and subtracting that product by your dividend. That's a lot of words. Let's check and see how we do that. I'm going to see how many times x goes into x cubed. In other words, x times what is x cubed? Well, this number is x squared. So this goes in x squared times. Now you're going to take this x and multiply by x squared. You'll get x cubed. Take the 3 and multiply by the x squared. You'll get 3x. Now what we're going to do is subtract. Okay? Now no matter what, just like when we did numerical long division, we looked in the thousands place, nothing was there. Looked in the hundreds place, we ended up getting rid of hundreds values here. In other words, we're only checking to see, we checked to see how many hundreds there are from this number. There are 3 hundreds. Then we checked how many tens. So we should be done with the hundreds afterward. Likewise here, when we subtract, we should be done with the cubics. So x cubed minus x cubed is 0. There's nothing up here combining with 3x. So 0 minus 3x is negative 3x. And there's a plus 27 there as well. Okay, let's check and see how many times x goes into negative 3x. That's a negative 3. Okay. So you go, I'm sorry, this is 3x squared. Let's do that again. This is red. Some color. This was 3x squared, 3x squared. This is negative 3x. Right here. So x goes into negative 3x squared, negative 3x times. You multiply that, get negative 3x squared. Again, these should always cancel. 3 times negative 3x is negative 9x. These cancel. 0 minus negative 9x is positive 9x. Bring down the plus 27. X plus 3. Okay, how many times does x go into 9x? That's 9 times. X times 9 is 9x. 3 times 9 is 27. Subtract, and we get 0. So your final answer here, this equals x squared minus 3x plus 9. Another way to write this is that x cubed plus 27 is x plus 3 times x squared minus 3x plus 9. Now you might have already known this was the answer because this is actually a sum of 2 cubes. If you think about it, this is a cubed plus b cubed. Make sure that you remember this. Okay, let's see. X cubed, that is x quantity cubed. 27 is 3 quantity cubed. So that's x plus 3a plus b times x squared minus 3 times x plus 3 squared, which is 9. So you see, those were the same thing. And that makes sense. We just did some long division even though we could have seen that was a sum of two cubes problem, in a way. But what you needed was this answer right here. I mean, this is the answer to your question. I'm just writing it in factored form. Okay, let's do another one here. Now this one's a little different because I have a 2x. We haven't done too much division with that. But I want to make sure you can see the difference in this with long division, with synthetic division, all that stuff. So here's 2x plus 1. Okay, 2x is your most significant term. I need to see how many times 2x goes into 2x cubed. Well, x squared times, of course, because 2x times x squared is 2x cubed. 1 times x squared is x squared. Terms combine. I have 0 here. 9x squared minus x squared is 8x squared. Bring down the 14x. Okay, how many times does 2x go into 8x squared? It goes in 4x times 8x squared plus 4x. Subtract, I get 10x. Bring down the 5. And finally, how many times does 2x go into 10x? 5 times. Multiply that. 2x times 5 is 10x. 1 times 5 is 5. I get 0. So your final answer there is x squared plus 4x plus 5. And again, if you wanted to write it in factored form, this whole guy, 2x cubed plus 9x squared plus 4x, 14x plus 5, equals 2x plus 1 times x squared plus 4x plus 5. If that's a part of what you're doing. Okay, polynomial synthetic division. Now this only works for linear factors. I should really start this guy. This is an important concept here. You can't do this unless you're looking at what one of your roots are. Need the root. Super important. Okay, the idea behind synthetic division, okay, is that you use that root value. And every root can be expressed as a linear factor. So for example, if you have a root of 2, x equals 2, your linear factor for that is x minus 2. Really, the other way that you do this, though, is if they say, for instance, I'll look at this example really quickly, you're dividing by x plus 3, well, your root then is negative 3. You're trying to see what value I am going to use over here. Okay. If you like to use synthetic by a quadratic expression, you must find your two roots first, even if they are irrational or imaginary. So an example, because this is also, let me get you started, because this is on your problem number 13 in your practice test. If you're dividing by this right here, okay, you need to figure out what some of your roots are here. You have x plus 4 times x minus 2. So two of your roots are negative 4 and 2. You can do synthetic division with negative 4, and then do synthetic division with 2 with your remaining polynomial. So this is a way that you can do this problem if you don't use long division. So it only works for linear factors. You have to break this up into linear factors at all costs. Okay, now synthetic division is kind of easier in that way. If you have your root, then it's a way that you can go about doing these problems, and there's no problem with it. But the only thing is, I want you to make no mistake, long division and synthetic division are the same thing. In fact, after I do these synthetic division problems, we'll tie them in exactly and see how the numbers relate. Synthetic division says basically this. We're going to remove the variables because we know how many times our divisor goes into our dividend. Basically, if you think about like this example right here, we're saying, remember when we did long division, we said how many times does x go into x cubed? We know how many times it's going to go in one. I'm sorry, these coefficients here. We know it's going to go in one time because this will always be an x out here. Because when we break this up as a when we make this a linear factor, it's going to be x minus something, x plus something, whatever. So this x will always be there. It's going to go in that many times to start, and then you're going to multiply your divisor term by this number, which cancels out, by the way. Notice how this always cancels out. That's what I kept saying. These cancel, these cancel, these cancel. Synthetic division says we know they cancel. So there's no reason to look at this x variable at all, other than say how many times the coefficient goes in with this coefficient. That's all we're going to look at. the only other thing that they say is that it also recognizes, because you're dividing your expression by a linear term, that your degree will always reduce by 1. So if you're dividing a cubic, if you're using synthetic division starting with a cubic, your answer is going to be quadratic. If you start with a quadratic, it's going to become linear because you're dividing by a linear term. This only works for linear factors, so you also know that. So these are some important things as we do this. So I'm going to go ahead and get started. Oh, actually, I need this note. It's important. 0 placeholder values are incredibly crucial to insert in your model. Because you don't have x values on display, you have to remember that like terms still need to combine. Be careful here. So let's do this. You've seen what synthetic division looks like, so I'm going to write it out. You're going to spell out your coefficients here in x cubed plus 27. There's a 1 and there's a 27. Now I'm not going to put them right next to each other because 0 placeholder values are super important. X cubed plus 27 is also x cubed plus 0x squared plus 0x plus 27. These zeros are so incredibly crucial because if you think about what I did way back here, this is the same problem. If you think about what I did here, notice how my 3x squared didn't combine with my 27 because they're not like terms. I shouldn't get like 24 or 24x squared or something here, and you would make that mistake here if you didn't have these zeros. You need to make sure you account for your x squared term and your x term when you subtract. So we're going to tie those in really after we do all this. I just want to make sure synthetic division makes sense here. Okay. I'm going to, everything you do here, you're going to add. Now this 1 is not going to be added with anything because once again, you're just checking to see how many times this x goes into this x cubed. The answer is 1x squared. It's just 1x squared. If this number was a 2, this would go in 2x squared times and your number would be a 2. But it's just a 1. Now you're going to take that negative 3 and multiply by 1. And you put it there. Now you're going to add again. And this will become a negative 3. You take that negative 3, multiply it by negative 3, and you're going to get a 9. Add again, you get 9. Negative 3 times 9 is negative 27. And add, and you get 0. Okay, now I will tie in how this long division match up completely perfectly on the next slide. But for now, I want to make sure I get through this nice and well. Now, this ends up, remember, this was a cubic, this was a square, this was a linear, and this was your constant. Now this becomes your square, your linear, your constant, and your remainder. Remainder is 0, your constant term is a 9, your linear term is a negative 3, and your quadratic term is an x squared. So that's x squared minus 3x plus 9 with a 0 remainder. Okay, so that gives you the same answer as you got over here, x squared minus 3x plus 9. Okay, so we're in agreement. Okay, let's do this one now. Now the important thing is you need to find the linear factor. Now this is a linear factor, but we need to find the root. What is the root of 2x plus 1? We need to set that equal to 0. And find out what x would be. Okay, we are allowed to add here by switching the sign, but it's not just switching the sign. You need to find out what that number is. This is negative 1/2. This might not be very fun. You have a fraction to deal with this time. Okay, this is where synthetic division sometimes isn't your favorite. You have to do some work beforehand. Now you have to deal with the fraction, and just make sure you don't screw up. 2 plus nothing is 2. 2 times negative 1/2. Ah, not so bad. That's negative 1. 9 minus 1 is 8. 8 times negative 1/2 is negative 4. See, that's not too bad. 14 minus 4 is 10. 10 times negative 1/2 is negative 5. 5 minus 5 is 0. So your remainder is 0. Here's your constant term, 10. Your linear term, 8x. Your quadratic term, 2x squared. Okay, so then you sit there and go, well, wait a second. How is this answer different from this one? And the problem was, you have to remember here, we divided 2 times this amount. Here we only divided 1 time this amount. When we got this root right here, yes, this was one of your roots, but if we write this as a linear factor, this really should be x plus 1/2. So this is what we divided by. We didn't divide by 2x plus 1. We didn't it's like factoring the 2 out. So you need to take this and divide by 2 unless you want to make sure that you wrote your factor right or wrong or whatever. But if you divide by 2x plus 1, you have to divide by the 2 as well. So do it in the beginning, do it in the end, do whatever you need to do, but this becomes x squared plus 4x plus 5, like that. So that's the tough part about this. That's really why long division is the key to, unless you have your linear factor spelled out exactly like this, 1x plus something, 1x minus something, then you might run into a little bit of trouble. Okay, what they look like, what they look like side by side. Let's go and do these. I want to rush through this a little bit more because I want to talk about remainders next. Long division. This time, if you saw the placeholders for synthetic division, they can help equally as well for long division too. If I do x to the fifth plus 1, I also want to include plus 0x to the fourth plus 0x cubed plus 0x squared plus 0x plus 1. The reason being, it's easier to subtract when you see exactly what you're writing over. So x goes into x to the fifth, x to the 4 times, multiply, plus 1x to the fourth, subtract 0, and negative x to the fourth. Okay? Plus 0x cubed, plus 0x squared, plus 0x plus 1. I don't really have to write all of those. Really, I just write the next term over, because this is 2 terms, so you're only going to be doing 2 terms max to combine. So really, what I'd prefer doing is just writing the next term, just like that. X goes into negative x to the fourth, negative x cubed times. You get negative x to the fourth minus x cubed. Remember, you subtract here, 0, and this is positive x cubed, because we subtracted negative. Plus 0x squared. X goes into x cubed, x squared times. Multiply that, you get x cubed plus x squared. You subtract. That's negative x squared. Bring down the 0x. X goes into negative x squared, negative x times, multiply. You get minus x there. Subtract, you get positive x plus 1, and x goes into x 1 time. You multiply, you get x plus 1 times x plus 1 is 0. And your final answer is on top right there. X to the fourth minus x cubed plus x squared minus x minus 1, or plus 1, no remainder. Very fun, very fun. Okay, synthetic division. Let's do the same thing. Here's your linear factor. Remember, it needs to come in x minus a form, and your root is x equals a. Okay, so my root is going to be negative 1. So when I do synthetic division here, I'll use a negative 1. This is 1x to the fifth plus 0x to the fourth plus 0x cubed plus 0x squared plus 0x plus 1. Synthetic division still works quickly here. Bring down the 1. Negative 1 times 1 is negative 1. Add again. Negative 1 times negative 1 is 1, etc., 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 etc. That looks kind of weird. What are these? Remainder, constant, linear, quadratic, cubic, quartic. Your final answer there would be that. Okay. How do these look side by side? Here's kind of what I wanted to tie in here. Where are these numbers coming from? Whatever else. This is kind of a bad example because all the numbers are the same. They're all ones. But I'm going to give colors here and describe where they're being put. See this 1 right there that became that 1x to the fourth? That exists right there. Okay, this says how many times it's going into it. It's going in that many times. And this is the part that you don't check, because we already know that this is a 1x right here. When we do synthetic division, we set it up specifically so that it's 1x plus something or 1x minus something. That's why we don't need to do a check with anything else. We know that when we add, we're just getting that number out. Then when you multiply, check this out. I'm multiplying this 1 by x to the fourth here, and I get 1x to the fourth. And remember how I subtracted? You know, I don't write the subtraction part, but this is actually subtraction. See that 0 minus 1? Well, that comes right here. I multiply this by negative 1, like I multiply this by positive 1, and here I add and here I subtract. So they become the same thing, and I know it's hard to tie in because all these numbers are ones. But this is where these numbers come from. How many times does x go negative x to the fourth? That's negative 1 x cubed times. Again, that's where this number comes from. They skip by that part because they say, we know that it's going to be that because we're multiplying just x by this thing. Okay? So the same thing there. This positive 1 is put right here. Now this looks like a negative 1 to you. But we did 1 times negative 1, put it there. Or I'm sorry, we put it right here. It looks like a negative to you, but remember, when we subtract, that becomes addition. 0 plus 1, 0 plus 1. Right? That becomes a 1x cubed, like that. So you keep going, and it goes through and through. But that's where those numbers come from. Synthetic division kind of takes an intermediate step. It kind of does this faux way of making things happen. It's not bad. It's pretty good. But there are certain rules to it, and you can kind of see, like when we did this problem right here, there's some iffy parts with it. And even when I talked about the quadratic thing right here, I have to break them up and stuff. Both of them have their charms. They really do. This can be quick when it's set up with a linear factor already. You got to be careful for zero placeholders as well. Just a lot of small things.